First, I start by importing the required libraries for the machine learning experiment. I import pandas for handling datasets and data frames. Then I import NumPy, which is used for numerical computations. From scikit-learn, import train test split to divide the datasets into training and testing sets. These libraries are form the foundations for the most machine learning workflows in Python. Then for the next, in this step we perform data pre-processing, which is a very important step in machine learning. Thus we handle missing values in the data sets for numerical columns like sepal width, cm sepal length, sepal width, petal width, and petal length. We replace any missing values with the mean of the column. This technique is called imputation. The reason we do this because machine learning models cannot work with missing values. Replace them with the statistically meaning values. For the fourth, in this step we convert the categorical labels into numerical values using label encoding. The species columns in the iris dataset contain string values like Setosa vesicola virginica. Machine learning models cannot directly understand test labels, so we convert them into numbers using label encoder. These labels are transformed into numerical values as 0, 1, 2. This allows model to process the class labels during training. For since the perceptron algorithm is designed for binary classification, we only select two classes from the dataset. Here, I filter the dataset so that it only excludes species 0 and species 1. By doing this, the problem becomes a binary classification problem where the model learns to distinguish between two classes instead of three. In this step, we define the input features and target the variable. The input features are stored in this variable h. These include sepal width, sepal length, petal width, petal length. These features help the model learn patterns in the data. The target variables, which is species label, is stored in y. So in simple terms, x is equal to input data, y is equal to output label we want to predict. Next, we perform feature scaling using standard scaler. Standardization converts all features so that they have means equal to 0, standard deviation is equal to 1. This step is important because different feature may have different ranges. For example, sepal length might range from 4 to 7, petal width might range from 0 to 2. If we do not scale that data, some features may dominate the learning process. So for the seventh one, now we divide the data set into training data and testing data. We use test split function. 80% of the data is used for training, 20% of the data is used for testing. Training data is used to reach the model, testing data is to evaluate how well it is done. Now we initialize the parameters required for the training. The perceptron model. First, we say the learning rate, which controls how much the weights change during each update. Then we define the number of epochs, which represent the number of times the algorithm goes through the entire training data. Weights as 0, bias as 0. Weights represent the importance of each feature, and bias shifts the decision boundary. These are the values that are counted. And in this step, we train perceptron model. For each approach, the algorithm loops through all training samples. For each sample, it calculates the weighted sum of inputs using the formula W into H plus B. Then the perceptron predicts the class label. If the prediction is incorrect, the algorithm updates the weights using the rule. After training the model, we display the final learned weights. Each weight corresponds to one feature in the dataset. These weights show how important each feature is in predicting the class. The larger weight means the feature has a stronger influence in the model's decision. Here we visualize the learning process using a graph. The x-axis represents the number of iterations or efforts, and the y-axis represents the training error. As the training progresses, the error should gradually decrease. Now we use the trained model to predict the class label for the test dataset. For each test sample, we calculate W into H plus B. If the value of Z is greater than or equal to 0, the model predicts class 1. Finally, we evaluate the performance of the model. We generate a confusion matrix which combines actual labels and predicted labels. Then we calculate important feature performance, accuracy, precision, recall, F1 score. Then these matrices helps us understand how well the perceptron classifier performs on unseen data.